in this lesson out of Classroom Mathematics. We are still busy with Chapter 5, Area and Perimeter, and today's lesson is Definition and Formula for Area. So what we're going to do today is we're going to go into deeper detail on the formulas for area. So far we've learned the formulas and we've used them, but now we're going to go about and see where they come from, how they are derived. And then we're going to go further and we're going to derive some formulas for the different types of quadrilaterals. So to start at the very beginning, we have an area of a square. So if we have a square that is its sides are 1 unit, which means both sides are 1 unit, then this represents a 1 unit squared. And this is the starting block for all of the area, all of the shapes that we find the area of. So 1 unit of area is defined to be the size of the interior of a square with a side length of 1 unit called a unit square. So all the shapes we're doing are basically these little blocks put together. So we'll look at the different shapes now and see how that all fits together. So we've seen the area of a square is just side times side, which is side squared. So moving on, we now move on to a region bound by a simple closed curve. Now, as you can see, here we have a few blocks. Now, these also include your whole block. So here we've got 1 square unit, 1 square unit, almost 1 square unit, and then even the fraction of units. So adding all of these together will give us the total area that this region encloses. So the area of any region bound by a simple closed curve is the number of units squared, including the fractions, covered by the region. Then further on, we look at a rectangle. So this is a slightly more clear. If I have all of these as 1 unit squared, then I can see there's a total of 8 blocks, which is each 1 unit squared. So this rectangle in total will be 8 units squared. And what we normally do, we can see there's 4 blocks and there's 2 rows of 4 blocks. So that's why we say if it's, for example, 4 centimeters and we've got 2 centimeters over here, that's why the area of a rectangle is the length times the breadth, because we've got 4 blocks times by 2 of the rows of 4 blocks, and that would give us 8 units squared, or 8 centimeters squared. So from the above definition, it is easy to see why the area of a rectangle is a product of its length and its breadth. So area of a rectangle is length times breadth. Then we move on to area of parallelogram. Now, just to recap, a parallelogram is defined by its opposite sides. Both of its pairs of opposite sides are parallel. So we also have this height. The height of the parallelogram is the perpendicular height between one of the sets of the opposite sides, which is parallel. Now, what we're going to do to derive the formula for the area of a parallelogram, we're going to take this triangle over here, we're going to cut it out, and then we're going to shift it and place it over there, which then makes it look like this. So now we can see that this actually forms a perfect rectangle. And now we can just use the formula for the rectangle. So I'm going to say that the area of this parallelogram is equal to the area of E, so E star, because that's just a new translated E, B, C, E. All right. So now to find the area of this, we know it's length times breadth. So we're going to say it's BC, this side here, BC, times by this height over here. All right. So this is then going to be the basic or our new formula for a parallelogram, we can see is we just take the base BC times by the perpendicular height, and that would give us the area for the parallelogram. So area of parallelogram is the base times the height. Then we go to the area of a triangle. So the first thing we're going to do is, if I have only this triangle, we're only given this triangle, then we take this vertex over here and we construct a line that's parallel to this base over here, and we go from C and we construct a line that is parallel to this BA over here. So what we then see is we've formed a parallelogram, right? So now, since we know what the area is for a parallelogram, we can then find the area of a triangle from there. But the first thing, before we start with that, we need to see that triangle ABC is congruent to triangle CE, or is this a D? CD or CEA. So triangle CEA. What that tells us is, if they are congruent, is that these two areas are exactly the same. So first of all, let's start with the area is going to be equal to half of the area of parallelogram ABCE. Because if these two triangles are equal, their areas are equal, then that means that this triangle will be half of it. So we simply say that it's half. And what did we see previously? We saw that the area of a parallelogram is just the base. So in our case, BC times by the height. So here we can see, here we formed the area of a triangle, as we know it, half base times height. So area of triangle, half base times height. Then for a trapezium, now a trapezium is a quadrilateral with one pair of opposite sides parallel. In the diagram, ABCD is a trapezium with AD parallel to BC. The height h of the trapezium is defined as the perpendicular distance between the parallel lines. To find the area of the trapezium, so this is how we start. We're gonna, if you have a trapezium, you divide the trapezium, you draw a diagonal and divide it into two triangles. So now that we have the formula for the area of a triangle, we can use that to determine what would be the general formula for a trapezium. So to start off, the area will then be equal to the area of triangle, let's say DAB, plus the area of triangle BCD. Alright, so now the area of DAB, so this is our height and this is our base. Now this height is constant over here between these parallel lines. So we have half times the base, which is AD, times by the height, plus, now the area for BCD, half times the base, and in this case this is our base BC, and our perpendicular height runs down here, and that's still h, so times by h. Alright, now to simplify this, we can actually factor out the half and the h. So let's write it as a half, and then AD plus BC times by height. So I've just pulled out the half to the front of the bracket, and I've pulled out the h to the over here at the back of the bracket. So this is our general formula for a trapezium, it's half times the sum of the two parallel lines times the height. And then the area for a rhombus. Now, a rhombus is a parallelogram with all four sides equal to each other. Since a rhombus is a parallelogram, the formula for its area is the same as that of a parallelogram. However, since all sides are equal in length, so are the heights. Alright, so in this case, what was the area for the parallelogram? We saw that the area was simply the base times the height. So this area is going to be simply the side times the height. Alright, and then we have area of a kite. Okay, so kite is a quadrilateral with two pairs of adjacent sides equal in length. In the diagram, ABCD is a kite with AB equal to BC, we've got AD equal to DC, diagonals AC and BD intersect at O. Right, so now to start to get the area of this, we're going to divide it into two triangles. We've got this triangle, so that's going to be the area of triangle ABC plus the area of triangle ACD. Alright, then the area of this triangle is equal to, now if we look at this as the base and this as our height, then it's going to be half times base, which is AC, times by the height, which is BO. Alright, plus half times the base, which is AC. So for this one, this is the base and this is the height. AC times by the height, which is in our case OD. Alright, now I can factorize this to simplify it, taking out the half and the AC from both of these terms. So half AC comes out, then I'm left with BO plus OD. Alright, so this BO plus OD is together is BD. So half AC times by BD gives me a general formula for a kite. It's basically half times the 2. So you see AC is this diagonal and BD is this diagonal. So to find the area of a kite, we just simply say half times the product of the two diagonals. And then we get to a circle. Right, so now to look at how to derive the formula for a circle, think of this circle as a pizza, for example. So what we're going to do is we're going to slice it into pieces. Then we're going to take the pieces and we're going to lie them out like this. All right. So every second piece we lie on face down, and then opposite direction all the other pieces that's not colored. All right. So if we look at this length over here, can you see that it's only every second piece is distance? So that means this length represents half of the circumference. And this length over here represents the radius. Now, if we've laid out our pieces like this, this could almost be a rectangle. So to get the area of a rectangle, we normally say length times breadth. So in our case, we're going to have the length as half of the circumference times by, and our breadth represented by r, the radius. Now we know the formula for the circumference. The formula for the circumference is 2 pi r. So we just replace the formula for the circumference there, and then we can simplify this formula. So the 2's will cancel, the r's multiply together, and we're left with pi r squared. So area of a circle is simply pi r squared. Now for example 1, this we determine the area of ABCD. So what is ABCD? It is a parallelogram, and we saw that the area of a parallelogram was just the base times the perpendicular height. But before we can actually work that out, we need to find the value for h. Now h lies in a right angle triangle, and we can easily use Pythagoras. So I'm going to say that first, to find h squared is equal to the hypotenuse side squared, 4,3 squared, minus 2,4 squared, and I've used Pythagoras. Then I can solve for h is equal to the square root of 4,3 squared minus 2,4 squared. So if we put that into the calculator, we get the square root of 4.3 squared minus 2.4 squared, and that gives us 3,57 to 2 decimal places. So 3,57, and we are working with centimeters. All right, so now we can say that the area, which we saw was just the base times by the height, is then, so our bases, this side is equal to this side, or we can treat this as the base, DC, so that's 6,5 times by the height that we just found, 3,57, and this will then give us, so I'm just going to say that times by 6.5, and that's equal to 23,19. So 23,19 centimeters squared. Example 2. Once again, we need to determine the area of ABCD. And what is ABCD? We can see that two pairs are parallel. So this is a trapezium. So the formula for a trapezium was half, and then half times sum of the parallel lines times by the height. All right, so before we can do that, we need to find the height. We see that this part is also unknown. So we need to find, let's start with the height first. We can find that because this is in a right angle triangle. So we have that h squared is equal to 15 squared minus 9 squared. And we have used Pythagoras. So this h is then the square root of 15 squared minus 9 squared. And this gives us square root of 15 squared minus 9 squared is then equal to 12. All right, so our height is equal to 12. Then we need to find x. So if this height is 12, we can find x also by using Pythagoras. X squared is equal to 15 squared minus 12 squared. And that's Pythagoras. All right, and then x is equal to the square root of 15 squared minus 12 squared. It's equal to square root of 15 squared minus 12 squared, and that's equal to 9. All right, we are working with centimeters. So if this is 9 centimeters, we have this as 9 centimeters. Now let's look at the formula for the area of a trapezium. We said it was half times the sum of the parallel sides times by the height. All right, so this is going to be half. Now the sum of these sides, so the one side is 9 plus the other side is 9 times 3. We've got 9, 9, 9. So this is plus 27 times by the height, which we said was 12. All right, so this we can simply put into the calculator. This will be 0,5, and then in brackets we've got 9 plus 27, and then times that with 12, and this will give us 216 centimeters squared. Okay, so that is the end of this lesson. You can now do exercise 15.2.